Okay, hello everyone, welcome back to another video. Today we're going to be looking at a really interesting integral that involves some recursion. And it's the integral from 0 to infinity of 1 over 1 plus x squared all to the power of n dx. Now of course our answer is going to have to be in terms of n, and I've defined our integral as I of n. And some of you who know about the beta function might recognise that with a simple substitution we can kind of evaluate it using that. But I don't want to use any shortcuts or things that you might have to know or not know. I'm going to rely on a solution that just uses the classic integration techniques and a bit of manipulation of products later on to give a really satisfying result at the end. So my first thought when I see a 1 plus x squared as somebody who likes trig subs is to do a trig sub. And of course 1 plus tan squared theta equals sec squared theta, so that seems appropriate, especially because our bounds are 0 and infinity, and that's going to fit really nicely for tan. So if we say that x is equal to tan theta, that of course implies that dx is equal to sec squared theta d theta. And if we think about our bounds, as x approaches 0, we want tan theta to approach 0, which means theta will approach 0. And as x approaches infinity, we want tan theta to approach infinity, which of course happens as theta approaches pi over 2. And so we rewrite our integral as sec squared theta d theta divided by 1 plus tan squared theta to the power of n. And of course our 1 plus tan squared is the same as sec squared, and sec squared to the power of n is sec to the 2n theta. So we can do a bit of simplification here. Given that 1 over sec is cos, we can rewrite our 1 over sec to the 2n theta as just cos to the 2n theta multiplied by sec squared theta d theta. And you may have noticed as well that actually this sec squared theta is also 1 over cos squared theta, and that we could combine that into a power of 2n minus 2, but we're not going to do that. And the reason is because I have the intention of integrating by parts, as that's something we often do with recursion integrals, and you'll see why in a bit. And why would I want to save that for integration by parts? It's because sec squared, of course, is the derivative of tan, and so when I'm choosing my dv for my integration by parts, this is going to be a really nice choice. So of course I'm saying that dv equals sec squared theta d theta, which means that v equals tan theta, and I've got to choose a u as well to differentiate, and my u of course must be cosine to the 2n theta. And differentiating this is quite simple, we just have to use chain rule. So the derivative of the inside, which is cos theta, is negative sine theta, and the derivative of the outside function just uses power rule, so we bring the power down to n, and we minus 1 from the power to n minus 1 d theta. So we've got to get ready to use our integration by parts formula, and that is of course uv minus the integral of v du. So let's write out our uv. Our u is cos to the 2n theta, and our v is tan theta. And this is being evaluated between the bounds of theta equals pi over 2 and theta equals 0. Now we can't forget our integral part, but before we write it down I want to pull out all the constants that we can outside of the integral just to tidy things up a bit. So of course our integral is of v du. There's no constants we can pull out of v because the only thing we've got is tan theta, and that is something that's with respect to theta. And in our u, we can't pull out sine theta, we can't pull out our cos theta, but our negative 2n we can pull out. And so since we're minusing, but we're minusing negative 2n, we're actually adding 2n times the integral from 0 to pi over 2 of du, which is sine theta cosine to the 2n minus 1 theta times our v, which is tan theta d theta. So the first thing we want to do is evaluate this part here. It's the part we've already integrated, and we just have to look at how it behaves between the two bounds. And I've rewritten it out just to make it a bit more clear using the colours. So as theta approaches pi over 2, tan theta approaches infinity, but cos theta approaches 0, and anything times 0 is 0, so at our upper bound we have 0. And using the same logic at our lower bound we also have 0, because whilst cos theta will approach 1, tan theta will approach 0. So this entire part of uv from our integration by parts is just 0 minus 0, which is of course 0, and so we can kind of ignore it. And so we now have that in is equal to this integral that we've integrated by parts, which is also equal to the following. But this isn't particularly nice, and we can do a lot of simplification here. So the first thing to notice is that tan theta is obviously sine theta over cos theta, right? And dividing by cos theta is the same as multiplying by cos to the minus 1 theta. And we've already got a cos to some power here, so we can of course bring our powers together. So when we divide by cosine here, we're going to subtract 1 from the power, and this is going to become cos to the power of 2n minus 2 theta. And we've got a sine here and a sine here, and so let's bring our sines together into a sine squared theta, like so. Now, since our integral is written in terms of cosine, I think it makes more sense to rewrite this as the integral from 0 to pi over 2 of 1 minus cosine squared theta multiplied by cosine to the power of 2n minus 2 theta d theta, as follows. And of course this is a bracket we can just expand out. So when we multiply by 1, nothing's going to change. We're just going to have the integral from 0 to pi over 2 of cosine to the power of 2n minus 2 theta d theta. And then of course for our second part of expanding the bracket, we still have our 2n here, and it's the integral from 0 to pi over 2 of cos squared times cos to the 2n minus 2. Now our powers are going to add here, and of course 2 minus 2 is 0, leaving us with just the 2n as a power. And of course we're integrating with respect to theta. So here's the relationship that we've been looking for. This is why we integrated by parts, because it gives us an integral in terms of an integral. And these two integrals should look familiar because we can write them in terms of in. Now firstly, this part here is the most familiar, because of course cosine to the 2n theta times sec squared theta is just the same thing as cosine to the power of 2n minus 2 theta d theta, which is exactly what we've got here. So that means this entire integral can just be written as in. So that's the first nice part that we've got. We've got the in is equal to 2n times in. And now we've just got to write this integral in terms of in as well. And if we factor our power of cosine over here, it's actually 2 times n minus 1 theta. Which means that if I were to swap my in for in plus 1, we would increase our value in the bracket here by 1, leaving us with just an n, and that's the integral that we've got over here, which means that this integral here can be replaced with I of n plus 1. It's going to be one step greater than the integral that we started with. And this is the crucial relationship that we've been looking for. Let's rewrite it out because it's so important. It's that in equals 2n in minus 2n in plus 1. But of course we're going to want this in terms of in plus 1, and some simple manipulation will yield the following. And of course if we just divide by 2n, we find that in plus 1 is equal to 2n minus 1 over 2n multiplied by in. But in a similar way to proof by induction, I want to find a starting point and build up from there. I don't want to have a formula in terms of in and in plus 1. I just want to have in terms of n on this side. And how can I eliminate that? Well, it's by thinking about what I of n is equal to for specific values. So let's go back to the start of this question. Now normally I'd choose n equals 0 as a nice starting point. We could build up from there, but when n equals 0 we have a problem, because 1 plus x squared all to the power of 0 is just 1, and so we'd be integrating 1 between the bounds of infinity and 0, and that's going to diverge. It's not something we can deal with in a nice way. So I'm going to choose the next best option. I'm going to choose when n equals 1, and that means we don't have to worry about this bracket at all. And this is going to be, of course, the very familiar arctan integral. It's equal to arctan of x, and evaluated between the bounds of infinity and 0 will yield pi over 2 minus 0, which means that I of 1 is equal to pi over 2. Now why might that be useful to us? Well, it's because if I have I of 1, to find I of 2, I just need to use my factor here that I'm multiplying by, which of course in this case is going to be when n is equal to 1, multiplied by my first integral, which I now know is pi over 2. And then when I want to find I of 3, all I've got to do is swap out my n's for an integer that's just 1 greater and multiply by my previous result. And my previous result, I2, can be expressed as what I just wrote. And eventually we'll end up with an entire sequence of fractions multiplying out, all starting at I1, which is pi over 2. And so this product of fractions, I'm going to write like this, that in plus 1 is equal to, well, of course, pi over 2, which is our first value, times the product from 1 to n of 2k minus 1 divided by 2k. So, how can we evaluate this product over here? Because I think there's some simplification we can do. Well, actually, let's think about the numerator first, because that's the hardest part. Our numerator, which I'm going to write in pink, is this product. It's the product from 1 to n of 2k minus 1. But there's a nifty way we can simplify this. It's by saying that that product times the product from 1 to n of 2k is the same thing as 2n factorial. And that might sound a bit confusing or like it's come out of nowhere at first, but really it's just because this product here is all of the odd integers up to 2k minus 1, right? So it's 1 times skip 1, 3, skip 1, 5, skip 1, all the way up to 2n minus 1. And this product is all the even integers multiplied together up to 2n. So it's 2, skip 1 times 4, skip 1 times 6, all the way up to 2n. And this sequence is clearly 2n factorial. And the reason we might want to write it out like this is because this product here of the even integers is so much easier to evaluate, because we're just doing 2 multiplied by itself n times, which is of course 2 to the n, and we're doing k when it's equal to 1 times k when it's equal to 2 times k when it's equal to 3 all the way up to n, also known as n factorial. And so that product is equal to 2 to the n times n factorial, and we just have to divide through by that, 2 to the n times n factorial, and that's what our product is equal to. So we know what our numerator is, we've just got to think about our denominator. Well, our denominator is just 2k, and we already just worked out how to evaluate that. That's just going to be 2 to the n times n factorial. So our numerator was 2n factorial. Our denominator that we've got left over here is 2 to the n times n factorial. And the denominator from our product evaluated is also 2 to the n times n factorial. And so there's just one final bit of tidying up we can do, and it tells us that I of n plus 1 is equal to pi times 2n factorial divided by 2 to the, well, we'll group our 2 to the n's into 2 to the 2n's, and of course we've actually got a pi over 2 here as well, so it's going to be 2n plus 1 multiplied by n factorial squared. So I hope you've enjoyed this video. I thought this was a really nice result because it's quite simple recursion, but it also comes together really nicely, especially that splitting up of the odd and even integers as their products. Let me know if you've enjoyed this or if you want to see any different content soon, and thanks for watching. See you later guys, bye.